Okay, so far this semester, we've covered linear motion, and that gave us our V final is equal to V initial plus acceleration times time. V final squared is equal to V initial squared plus 1 or plus 2 times acceleration times my change in position. We've done my change in position is equal to my initial times time plus 1/2 my acceleration times time squared. We've done angular motion, where this is going to be in our angular items. There's my change in angle. So we had our angular motion. We've done force is equal to mass times acceleration. Those are vector quantities. And we've done torque is equal to my moment of inertia times my acceleration. So we've done that. We've also done over here, F is equal to G M1 M2 over R squared. So we had that one for our law of gravitation. We don't have something here for the angular version of that, but this one will come in. We do get my centripetal acceleration can be V squared over R. And that does kind of correspond to my angular motion. We have linear momentum, which is mv, and then we have angular momentum, which is Li omega. We've done, let's see if I can get that to focus just a little better. That's better. So we've done our angular momentum and our linear momentum. We've done conservation of energies, so we can conserve mass, energy, momentum, and that's both linear and angular. We've done kinetic potential energy is mgh. We've done kinetic energy, which is 1/2 mv squared. But if I were over here with my angular one, this is kinetic energy due to rotation, which was 1/2 I omega squared. We have some items associated with springs. We did our force is equal to minus kx. And we have our kinetic energy due to a spring, which is 1/2 kx squared. I'm trying, let's see, we've done vectors. So my vector would be, if I did this as a capital V vector, this is going to be AI plus BJ. And we have independent motion in my vectors. Just to make our chart. So if you wanted to create your own cheat sheet, we want to put in our trig items. This is my hypotenuse. This is my opposite. This is my adjacent. And we have the sine of the angle is the opposite over a hypotenuse. Cosine of the angle is my adjacent over the hypotenuse. And tangent of the angle is my opposite over adjacent. And I think that about covers everything that we've done so far. So you have it as one lovely little sheet that you can look at. So now, basically what we've done is given you some kind of the rules. So one of the things we're going to go off of is that we talk about mass, and we said mass was matter, and mass was different than weight, because weight is a force. So if I were doing it in the English, weight is equal to pounds, and SI, weight, is in newtons. But my mass, what we've seen so far, is that mass is related to inertia. If I have the bigger the mass, the more force I have to apply to get it to move. But this inertia also can be linear or rotational. And that gave me my weight as mg. This gave me my moment of inertia, which is going to be my mass r squared, depending on how I was doing that. And if I were doing disks, so if I had a disk, we are adding up all these incremental little items of mass to relate it back to my moment of inertia. And remember, for a disk, my moment of inertia worked out to be 1/2 the mass of the entire item, the radius of my circle for a disk. But this is related, these individual masses get us what we're needing. So one of the things that we know is that mass can neither be created nor destroyed. Oh God, I can't spell again today. It's Friday. So mass is the stuff of the universe. And we just recently figured out that we haven't been, well, we knew we weren't accounting for all the mass, because we knew that, but based off of what we could theoretically determine, things were not quite working, so we hadn't found all the mass. And now with the James Webb Telescope, we're actually seeing some of the mass that we didn't know was out there. So that's kind of pretty cool. So now we're sitting there going, all right, if we're in my realm of the world, as my husband and I were talking about, we think of mass, we think of elements, and elements like gold, silver, copper, carbon, sodium. These are the smallest units that have unique physical properties. Because we know that gold has got a different density than silver. We know those are going to have different reactivity. We know they're going to have different, with some of these will make cations, some of them will make anions. We know a lot of things about these materials, And we can come up with a periodic table that has those unique properties associated with those materials. But physicists take it a little further. This is where I start to play, okay? I'm a chemical physicist, so elements are where I start looking at my world, but we are going to take it a little bit further down because physicists actually go into what makes these things. And so we know from experience, and because most of us have taken chemistry, that an atom is comprised of a nucleus. And in that nucleus, I can have some protons and neutrons. So let's give ourselves that. And then I can have little electrons hanging around on the outside. So my nucleus is made up of protons and neutrons, and my electrons are out there. So then we take our things like our protons and we send them into a super collider, and we find out that protons are made up of other fundamental particles. So let's look at the building blocks of matter. Okay, so we're going to look at the building blocks of matter. In Blackboard, you've got some helpful pieces of information that are out there looking at stuff, but we're going to start looking at these building blocks. So we actually have items that we call quarks, and physicists are a little strange in that we will argue in letters to the editor over 6 months whether this word rhymes with park or this word rhymes with pork. And you go, okay, I don't need to worry about that. But when we break up a proton, protons and neutrons are made of quarks. And it takes 3 quarks to make one of those. And my quarks are going to have fractional charge. That's why I'm going to either get a neutral charged neutron or I'm going to get a positive charged proton. But my quarks have unique names. They're up and down, charm and strange, top and bottom. And you need 3 of these to make up a proton and a neutron. We also have some particles that we call leptons. And we're going to get, this is the electron neutrino. This is our muon neutrino. This is our tau neutrino. We have an electron. An electron is a fundamental particle of the universe. So there's our electron. We have a muon. And we have a tau particle. Then we have force carriers. This will be our photon, our gluon, and we have the Z boson, and we have the W boson. And these are things that Dr. Hageb has been studying. So kind of an interesting thing that folks are there. So these items here are the things that are going to be the fundamental particles of the universe. And these are kind of unique things, and they have interesting properties, and it's supposed to help us explain how we ultimately make up matter. But for me, I don't play in this world. This is world that I don't play in. I start when we deal with the atoms. That's where I start. But I at least want you to see that there are other items that we have. And this world gets a little strange. They actually, we start doing string theory, we start bringing these together, we start doing a lot more mathematics in order to get those. But these are all kinds of interesting items. But we're going to go back to our atoms because atoms are nicer and they're easier to deal with. So we have our experience with our lovely atoms. And atoms give us our elements. And we know we can define our periodic table. So I'm going to draw my outline of the periodic table here. So there's my outline of our periodic table. Over here, we have our noble gases. Then we have our metalloids, or what we've got. So these are our non-metals over here. And these are our metals over here. We get cations on this side. And we get anions on this side. And we know that things in columns are going to have similar properties. Right? And we also know that my atoms are going to get bigger as we go down to down the periodic table, and we can start playing with a variety of interesting things and how these things are going to interact as we start putting all our physics rules together. But these are going to also have physical properties, and our periodic table is the ultimate cheat sheet. Because when we start looking at our physical properties, we're going to have the actual mass. We can look at conductivity. We can look at things like resistivity. We have density. We got size. So we can start doing a whole lot of different properties associated with it. Let me finish writing out my word, properties. The other thing that we know about these items is that they're going to be in different physical states. Now, in our physical states, these are going to be what we normally see. So these are normal, and so normal would be standard temperatures and pressures. Okay, that's my standard temperature and pressure. And my standard temperature is going to be 0 degrees Celsius, and my standard pressure is 1 atmosphere. And so we have our normal states of matter. So we've all been to chemistry class. We've all been through elementary physical science, all that kind of stuff. And we talk about normal states. So when we think of normal states, if I'm in chemistry class, we're going to say that our normal states of matter are gas, liquid, and solid. Now that's chemistry class. In physics class, we're going to add something else. We're going to add a plasma. And so let's define our gas first, because we know about gases. So if I have my balloon and I put my little molecules in here, or my little atoms or my little elements, they're going to fill up the space. And so gases are going to be, they're going to be less dense. They're going to be very open space. So there's lots of open space. They're going to fully take up the space in their container. And we usually think about these things as being, there's lots of empty space. And we do a lot of definitions for ideal gas. Now, plasmas are unique. Plasma is an ionized state. And it's got an overall neutral charge. But it has electromagnetic properties. And you can actually control it. So we think of plasmas, you know, you do experience plasmas and all kinds of things. The most common place where we're going to experience a plasma would be in a neon light tube or a fluorescent light tube. We're generating a plasma that gives us that ionized state. It's going to give us, you can actually get plasmas that'll form balls in there. You can get some strange things. But plasmas are kind of strange, and so it is definitely a different physical state. Now, solids, we tend to think of solids a little differently. Solids have a standalone shape. All right, and typically we think of a solid as having regular crystalline structure. So if I were to build a salt, good old sodium chloride, I know that my atoms are going to be in this nice crystalline structure, and we're going to have that nice, beautiful crystalline structure. And it's going to behave in a certain way. That's usually how we think of solids. However, my cell phone is a solid. It doesn't have a normal crystalline shape, but I do have my cell phone as a solid. We do have that there. We know a piece of wood is going to be a solid. So we typically think of a solid as having a standalone shape. Now, liquids are a little interesting. Okay. Typically, we think of a liquid, it's going to take the shape of its container. But we've just used that definition for a gas. What makes liquids different is that we get an interface. They're going to have a defined interface. And we're going to see that there's going to be some interaction between the individual components. In my gases, I don't get that interaction between the individual components. So I'm going to have that with a defined interface. So I can tell the difference between a gas and a liquid because of that defined interface. So in chemistry class, we normally tell you there are 3 states of matter. In physics class, we tell you there are 4 states of matter. And I'm going to tell you we lie to you. We lie a lot. And for most things, you can divide them into solids, liquids, and gases. But we have other things as well. So let's think about what some of those other things are. So I'm going to give you an example. So if I take a glass of water and I shine laser light through it, I'm gonna get a pattern on the wall that's gonna look like this. It's not, it's gonna be a nice speckle pattern. There's no defined shape. If I do a pattern on the wall here, I'm gonna get definitive dots. That's how we can tell what our crystalline structure is. So this solid, if I scan an X-ray through there, I'm gonna get an X-ray diffraction pattern and I'm gonna get a nice defined shape. If I shine a laser light through a glass of water, I'm going to get that kind of a pattern. Well, it turns out if I do the same thing with a piece of glass, which we would normally say is a solid, I'm going to get the same diffraction pattern. I will not be able to tell the difference by this diffraction pattern if I'm sending the light through a liquid or if I'm sending the light through a piece of glass. This has what we call an amorphous structure. In fact, if I were to draw my structure of water, so here's my good old water molecules, right? These are all going to kind of be out here together. I'm going to get hydrogen bonding, which is what's going to allow my water to actually stay together. Over here, if I'm using silica, silica will be like this to another silica, which will be down here like this, and it'll be over like this. And I get a structure that's very random. And that's why I'm going to get those same types of patterns. Well, this amorphous structure is going to behave very differently. Think, for example, about carbon structures. Carbon has many allotropes. Allotropes. Okay, carbon has a lot of allotropes. And that means carbon can come together and form a variety of things. So we can have carbon in the form of coal. And we all know what coal looks like, but that's carbon. You get a lump of a charcoal briquette. Carbon can be in the form of a diamond. And that's going to have a nice, solid, regular structure, would meet our definition of a solid really, really well. We get a nice, good crystalline structure. Coal's not as crystalline, but it's got a better structure than normal. We get graphite. And we get all the different buckyballs. So we get all kinds of different allotropes. And what an allotrope is, it's a different type of physical state for the material. Now, what's interesting about carbon is this graphite is the softest on what we call the Mohs scale when we're measuring hardness of different different minerals and things like that. And diamond is the hardest on our Mohs scale. So it's kind of interesting that it's the same element that's going to give me the softest and the same element that's going to give me the hardest, because my graphite actually this is a two-dimensional solid. And I'm going to get lots of what we call slip. I'm going to get lots of slip. It's going to be more amorphous. It's going to be able to break up. We can actually use graphite as a lubricant, whereas I can use diamond as a cutter. So I'm going to get different behavior between those two materials just because of its physical structure. So this amorphous structure for my pane of glass actually has a specific state of matter, and that's glasses. So glasses are a different state of matter. They're somewhere between solids and liquids. Some glasses will flow. We know that liquids will flow. Liquids will have flow. So I get glass that will come in here between this. So that's one example of where we've lied to you. Here's another example of where we've lied to you. Silly putty. Is that a solid or liquid?
I would say both.
It's something in between. Actually, it has its own state of matter, and we call those gels. Gels are another special state of matter. In fact, gels can be really interesting because gels can actually have a very defined crystalline structure. If you think of their hydrogels, hydrogels are going to be more solid. They're very defined. And so we get that one as well. So gels are kind of between our solids and our liquids. So there's another one that we have. In fact, right now there's a debate. We have somewhere between 9 and 13 identified states of matter. And there's lots of arguments between that 9 and 13 because several of them, like 11, 12, and 13, are all related to this situation. As we get cold and we approach absolute zero, which would be 0 Kelvin, as we approach 0 Kelvin, what happens to our atoms is that they're going to cease moving. And that gives us our kinetic theory of gases, which we've all talked about in chemistry. And they're all going to stop moving and they're going to order on our flame. And we're going to get what they call Bose-Einstein condensates. And that's as we get to absolute zero. What's going to be really interesting is when we ultimately get to absolute zero, we will not be able to distinguish between one atom and another atom because they're going to be in the exact same energy state. And then we get really bizarre types of behavior. So the question is, Bose has predicted a certain condensate. Einstein's predicted a certain condensate. We're talking about a lot of different groups. So the question is it all one structure or is it something different? The good news is we never have to worry about it because I don't know about you guys, but I'm not playing at absolute 0 Kelvin. That's not where I'm playing, and most of us aren't going to be there. Most of us are only going to have to deal with solid liquids and gases. And maybe plasmas, because if we had a plasma TV and we got plasma lights, we might have to deal with that. I, however, during my research, played with glasses. I looked at a lot of glass-like behavior and looked at the intermolecular forces of materials that produce a glass. So glasses were important to me. And actually, when I was developing my theory for some of the interparticle or intermolecular forces, that phase change between a liquid and a glass was very important to me. So those kinds of areas, glasses and gels, and actually gels are getting, from a medical point of view, these things like hydrogels, gels that are being used to help with wound treatment. Gels are becoming very important because they're actually providing structure, and we're going to be able to see some different behavior. So as you guys are moving through your various things, gels may become more important. But if I were to ask you on a test, how many states of matter are there? You're going to tell me it's physics class and there's going to be 4. If I were to ask you on a test in my chemistry class, how many states of matter are there? You're going to tell me 3, because that's just our normal operating atmosphere. But I want to tell you that as we develop theories and we develop the scientific method, and as we move through that, we always are going to do things that we're going to simplify things to tell you, which we did. And I told you guys that went back when we did forces, we said that this was Newton's second law. Newton's second law was the summation of all my forces was going to equal mass times acceleration. That's the simplified version. That's the most common version. We said, no, 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 that's not what Newton really said. Newton really said that I have an impulse is going to equal a change in momentum. And that's really what he said, because this definition is broader than that definition. And then we talk about the special cases. Well, the same thing happens when I'm dealing with fluids and materials and looking at our structures. And so we really want to play with that and understand that materials come in different structures, but for most of our stuff, we aren't gonna do that. So let's start dealing with some material things. Hey, I was gonna go somewhere. Oh, I want to talk about fluids. Because fluids are going to deal with the motion of the material. Because gases are fluids. Liquids are fluids. And we can actually fluidize solids. So fluids are going to be related to the motion of the material. Now think about my gases, and we're going to actually talk about this a little bit later on, probably next week, but here's an airfoil. So I have an airfoil, so this is a wing of a plane. As my plane, as my wing is flowing through my air, I'm going to get motion over my wing. And ultimately get lift. But my air is going to flow over the airfoil. Now, turns out that's also how a hovercraft works in water. So this could just as easily be water flowing over that, which is a liquid. Now, when we say we can fluidize solids, I don't know if you've ever seen this before. I can fill a container with, you can do it with flour. You can do it with sand. And I can put an object on here and I start vibrating the table. My block will disappear. The other way I can do that is I can bubble air through it. So I can send air bubbling through it. And my block will disappear. And this is fluidization. And we actually use this to do chemical reactions. We actually do this to help move things. We actually do this to help put pilings into the ground in some cases. So we can take solids and do either vibrate it or air bubbles or do something with those solids as long as my particles are smaller size and they're not in a crystalline structure, and I can actually have items move into things. So fluids, when we talk about fluids, it's more of a material property where we're dealing with the motion of the material. And we're going to look at that a little later as we start working with this material. All right, so let's start back with our good periodic table. And for those of you who don't know it, I am a chemical physicist. I looked at interparticle forces between particles on the nanosize scale. That's what I actually did. So let's use, we're going to go ahead and take an element from my periodic table. I've got iron. It has an atomic number of 26. It has an atomic molecular weight of 55,845, which is that all is going to tell me that we have 26 protons. For a neutral atom, we're going to get 26 electrons. And this molecular weight is more closely related to the number of protons and neutrons. Because remember, my protons, I don't have anything that's handy, but my electrons are 10 to the minus 31. My protons are much higher, so protons are definitely much heavier, and protons and neutrons have almost the same molecular weight. So that's going to be related more to the number of neutrons and protons. But my atomic mass unit, or my molecular weight, relates back to, so this would say I have 55.845 grams per mole. Or it says that if I have 6.022 times 10 to the 23rd atoms of iron, it will have a mass of 55.845 grams. And our mole is defined based on carbon 12. But, so that is, if I have 55.85 grams of iron, I have 6.022 times 10 to the 23rd atoms. But this occupies space. And then we start talking about density. Density, we use a rho to signify density, and we define density as mass per unit volume. And density in our world is going to be kilograms, meters cubed. All right. In your appendix, of the text, you've got common volume calculations. So if I have a structure that looks like this, the volume is going to be length, height, width. Length times the height times the width. I'm going to end up with meters times meters times meters. I'm going to end up with meters cubed. If I have a sphere, the volume is going to equal 4/3 pi r cubed. If I have a cylinder, that the volume is going to equal pi r squared h, where this is the area of the circle, times the height. And there are other structures, there are other common structures that we use, but you can actually, if you're calculating densities, you can actually use those. So those are common. Density is also going to be related to specific gravity. And specific gravity is the ratio of density of the material to the density of water. And we use water to help us do some definitions, and the density of water is equal to 1.0 times 10 to the third kilograms meters cubed. And actually, we use water for a lot of things, because we define 1 gram is equal to the mass of 1 cubic centimeter. So I'm going to write that out. Of water. So 1 gram is the mass of 1 cubic centimeter of water, and 1 cubic centimeter is equal to 1 milliliter. So we use water to give us a lot of our defining types of items. So we have a box. And our box is 1 meter tall, 0.5 meters wide, and 2 meters long. It has a mass of 1.5 kilograms. We want to calculate the density. Well, density is equal to the mass divided by the volume, and I've got 1 meter times 0.5 meters times 2 meters, and that's going to give me 1.5 kilograms meters cubed. Okay, we're going to do a problem here. So we all know this is the fun part, right? So I have a 150-pound person that's sitting on a stiletto shoe. And we're going to put all that weight onto the heel of the shoe. And the area of the shoe is going to be 1 inch squared. Conversely, we have a pony here. And my pony is 900 pounds. And its foot is 16 inches squared. And all the weight is on that front foot. Which one do you want stepping on your foot? So all the weight of the person is going to be on the stiletto heel, or I have all the weight of the horse on one hoof and it's stepping on your foot. Which one do you want to have step on your foot?
The shoe.
Okay, I got the shoe. So think about that for a second. Okay. I'm going to take the pony every day because this is our idea. We're going to define an item called pressure. And pressure is defined as the force per unit area. This is what allows us to use snowshoes and walk across snow. It's what allows us to do everything. So if I calculate the pressure that's being applied here, so the shoe is going to be 150 pounds per square inch because it was 1 square inch. The horse is 900 pounds over 16 squared inches. And, oh, okay. I have to do that calculation. I said, oh, I don't need my calculator because I've already got it all in all my notes. And well, you know, we all have rough days. $900 divided by 16. That's only 56.25 pounds per square inch. This one will break your bone. This one will just hurt. This one will just hurt. And to be perfectly honest, this is a quarter horse. And right now, if we were to do, and by the way, that right there, that's a size. This is a size 1 horseshoe. Just so you know, it's a size 1 horseshoe. If you want to have, we have a very dainty pony. She's very dainty. Her name is Ginger. She fits in a very small space. Ginger's probably 2,200 pounds. She's not quite a heavyweight. She's just kind of a lightweight, and she's really, really dainty. And she wears a size 4 draft. And a size 4 draft is, it's going to be, yeah, her foot is about a foot across. So hers is going to be 144 inches squared. So if she were to step on you, with all of her weight on her little dainty self, it's only going to be about 15 pounds per square inch. So, and what's really amazing is every draft that I've had, my half draft, he was also very dainty. He was only 1,800 pounds because he was a lightweight. He's half Arab, half Percheron, and he is a lightweight. But he would actually, their feet are so sensitive that he could tell if he was putting his foot on top of yours. And he wouldn't actually, he's the only horse I could ever go around barefoot because he would not step on your feet, just would not do it. But yeah, no, I'm staying away from stilettos all day long. Staying away from stilettos. So common units of pressure are going to be pounds per square inch And that's where we usually see it, and that we usually see it as PSI. So when you're filling up tires and stuff like that, you'll see PSI. In the Newton's world, this is Newton meters squared, and that's gonna be defined as a Pascal. And that's where we're gonna stop today. We'll pick it up there on Wednesday.